Good morning, dear students and friends. I welcome you in the lecture series of subject 303106103, that is Triple E. We are discussing the chapter number 1, that is DC circuits. In this lecture, we will solve one sum using the Thevenin's theorem. So, let's see the statements. Find out the current through 1 ohm resistance using a Thevenin's, Norton's and superposition theorem. First of all, we will consider the Thevenin's theorem. So this is the circuit diagram. Between node A and B, the load resistance of 1 ohm is connected. Between node A and D, 1 ohm current source is connected. Between node A and D, 3 ohm resistance is connected. Between A and C, 2 ohm resistance is connected. Between C and D, 1 volt source. Between B and D, 2 ohm, and between B and C, 2 ohm resistances are connected. See, in this figure I have given the name of the node, but generally in the figure the name of the node, principal nodes are not given. So you have to in the first step you have to decide the principal node. What is the meaning of principal node? Principal node is a node at which more than two circuit elements are connected together. So see, this is the principal node C. At this node, 2 ohm resistance plus terminal of the battery and 2 ohm resistances are connected. So 3 elements are connected. At this node, 2 ohm resistance, 3 ohm resistance and negative of the battery is connected. So 3 terminals are connected. So it's a principal node. This is also a principal node, node B. And between node A and B, the load resistance is connected. See, this node and this node are same because between these two nodes no resistance is connected. So as there is no resistance is connected, the potential of this node and this node are same. So actually it is a simple single node B. Similarly, this node and this node A both are same because there is no resistance is connected between this node and this node. If the resistance is connected between these two nodes, then there will be some voltage drop, and as a result the potential of this node and this node would be different. But in this case potential of these two nodes is same. Okay, so for applying the Thevenin's theorem, the first step is remove the load resistance 1 ohm, right, between terminal A and B. Then we have to find out the Thevenin's equivalent voltage, that is known as VTH, and we have to find out the Thevenin's equivalent resistance, that is known as RTH, right. So first of all we will find out the Thevenin's equivalent voltage VTH. So we have removed the load resistance between terminals A and B. So remaining network remains same like this, right? And now in step number 2, we will find the Thevenin's equivalent voltage, which is known as VTH, which is also known as VAB. It means the potential of A with respect to B. So for any complicated circuits, for finding out the VAB, it means what is the meaning of VAB? Find out the potential of A with respect to B. It means start your journey from A, take any path and ultimately reach to point B, and in between take the algebraic additions of the voltages or voltage source or voltage drops, right. So it is the meaning of VTH or VAB. But see, in this case, in this resistance, we don't know the voltage drop. So for finding out the voltage drop in each resistance, we have to either apply mesh analysis or nodal analysis. In this case, as the voltage source is available, I will prefer the mesh analysis. But the problem is that there is a current source. So current source should be converted into the voltage source before applying the mesh analysis. And you notice that this current source is connected in parallel with the 3 ohm resistance. Why it is connected in parallel with the 3 ohm resistance? Because as per the definition of the parallel connection, if the two circuit elements are connected between the same principal nodes, then you can say that the two circuit elements are connected in parallel. See, this 3 ohm is connected between A and D. This 1 ohm 1 ampere current source is also connected between A and D, right? So both the circuit elements are connected between A and D principal nodes. That's why we say that 1 ampere current source and 3 ohm resistances are connected in parallel. And recall the source transformation. Current source in parallel with the resistance is equal to the voltage source in series with that resistance, and that resistance is 3 ohm. And what is the magnitude of voltage source? Voltage source is equal to current source into parallel resistance, so 1 into 3, so it is a 3 volt. And see the direction of the current source, it is upward means upper terminal is positive, so in battery upper terminal should be positive, lower should be negative. If the direction is in downward direction, then the downward terminal would be positive, so downward lower terminal of the battery should be positive, upper terminal should be negative. So be cautious, right? Depending upon the direction of the arrow, put the positive and negative sign in the battery. So this current source is converted into the voltage source in series with the resistance between terminals A and D, right? If you want to apply the nodal analysis, then nodal analysis requires that it should contain the current source. Then convert the voltage source into the current source. Then voltage source in series with the resistance is considered as the current source in parallel with the resistance, right? So both the transformations are equivalent to each other. So our original circuit, this is converted into, right, current source in parallel with the resistance is voltage source in series with the resistance. Voltage source in series with the resistance. Rest circuit is same, right? And we have removed the load resistance between A and B. So this is the equivalent circuit diagram after the source transformation, right? Now we want to find out VTH. Now we can apply the mesh analysis. So this is the first mesh A C D A, and this is the second mesh C B D C. And see this A C B B A, it is the open circuit, and open circuit cannot be considered as the mesh. So this circuit contains only two mesh, 1 and 2. Now in each mesh assume the direction of current. I assume the direction of current I1 as clockwise. You can assume it as anti-clockwise, no problem. I assume the direction of I2 in second mesh as clockwise. Now we write the mesh current equations for each mesh. So generalized equations are this: R11 I1 plus or minus R12 I2 plus or minus R13 I3 is equal to plus or minus V1. So this is the generalized equation for the mesh current, mesh number 1, if the circuit contains 3 meshes. But in this case it contains only 2 meshes, so there will be only 2 terms, and it would be R11 I1 plus or minus R12 I2 is equal to plus or minus V1. Now let's see what is R11. R11 is the sum of the resistances in mesh number 1. So mesh number 1 is this, sum of the resistance exist in mesh number 1. So 2 plus 3, 5 I1. So it is 5 into I1. Then plus or minus R12. Sum of the resistance is common in mesh number 1 and mesh number 2. So R12, 1 and 2. Sum of which element is common? This branch CD is common in mesh number 1 and mesh number 2. But this branch CD does not contain any resistance, it contains the voltage source. So R12, sum of the resistance in common to mesh number 1 and 2 is 0. It is 0. And it is equal to plus or minus V1. So R11, 5 I1, R12, it is 0, I2 is equal to plus or minus V1. Algebraic V1 means algebraic addition of the voltages in first mesh. Now let's see what is the meaning of algebraic addition. Now, okay. See, in mesh number 1, we assume that I1 current is flowing and its direction is clockwise. Now, there are two voltages available in mesh number 1. It is 3 volt and 1 volt. Now, we have to consider its sign, whether it is positive or negative. So, to consider the sign, assume that at a time only one source is acting. So, let's say there is no 1 volt source, there is only 3 volt source. So, if there is a 3 volt source in the circuit, then this 3 volt source will supply the current from positive to A to C, C to D, D to negative to A. It means 3 volt source will supply the current in clockwise direction in this mesh number 1. And the direction of assumed current I1s is also clockwise. So as the direction of current which is supplied by 3 volt and the direction of assumed current I1 both are same, both are clockwise, we consider this voltage source as the positive voltage source. Please ponder on this concept, and if you have not understood, then see this video. Right? So 3 is considered as positive. Now we have to consider the sign of the 1 volt energy source which exists in the first mesh. Okay, again, when I want to consider 1 volt, at that time assume that this 3 volt does not appear in the circuit. Now, if in this mesh number 1 only 1 volt source exists, then the current will flow from positive to C, C to A to 3 ohm, to positive to negative to D to negative. In other words, the current supplied by 1 volt source will flow in anti-clockwise direction, and the direction of assumed current I1 is clockwise. Now both the directions are opposite to each other. That's why 1 volt will be considered as negative, because the direction of current supplied by 1 volt is anti-clockwise, whereas direction of assumed I1 is clockwise. So both the directions are opposite to each other. 1 volt is considered as negative and 3 volt is considered as the positive. Right? So algebraic addition of voltages in mesh number 1 is 3 minus 1. So this is the meaning of algebraic addition of the voltages in mesh number 1. So V1 is 3 minus 1. 3 minus 1. So simplify this equation, I1 would be equal to 2 by 5, so it is 0.4 amps. As we have obtained the positive answer of I1, so what is its meaning? Our assumed direction is correct. Assumed direction is clockwise. So I1 is actually flowing in clockwise direction in mesh 1, right? Because we have obtained the positive answer. And the conclusion is, if we have obtained the negative answer in I1, then the conclusion is our actual direction is opposite to the assumed direction. So in that case, I1 would be flowing in anti-clockwise direction. Okay, so we have obtained the mesh current I1. Now let's obtain the mesh current I2. So apply the mesh current equation in mesh number 2. So it is plus or minus R21 I1 plus R22 I2 is equal to plus or minus V2. So R21 I1 is what? Sum of the resistance is common to mesh number 2 and 1. Between 2 and 1, so there is no resistance which are common to 2 and 1, so it is 0. And remember, R12, it is what? Sum of the resistance is common to first and second mesh. R12 and R21 both are same, right? And it is 0. Then R22, sum of the resistance is in mesh number 2. So R22 mesh number 2 with this 2 plus 2 4I2. 4I2 it is equal to plus or minus V2. Sum of the voltage is in mesh number 2. How many voltages are there? Only one. And 1 volt source will apply the current in which direction? Positive to C, C to B, B to D, to negative to C. So it means in clockwise direction. And the assumed direction of I2 is also clockwise. So both the directions are clockwise. As the both the directions are same, we have to consider plus V. We have to consider positive 1 volt, positive V, plus 1, plus 1. So I2 is obtained as 0.25 amps. Again, as we have obtained the positive answer of I2, the conclusion is the actual direction of I2 is same as that of assumed direction of I2. So actual direction of I2 is also clockwise. Okay. So now we have obtained the mesh currents. So once the mesh currents are obtained, we can find out the voltage drop in each and every branch. And you can select any path as I told earlier. So now we can find out the Thevenin's equivalent voltage, that is VTH, that is VAB. So I can select this path, A to 3 ohm resistance, then A to D, D to B, right? This is the first path. I can select this path, A to C, C to B, second path. Then I can select the third path, A to C, C to this voltage source, to D, D to 2 ohm and B, right? So you can select any path, and then we have to take the algebraic addition of the voltages. So in this case I have considered which path? Okay, I have considered the this one path, A to C, C to B. So in AC branch, in 2 ohm resistance, which current is flowing? I1 current is flowing, and we have shown that the direction of I1's magnitude is 0.4 and its direction is, it is a positive, so actual direction is same as that of assumed direction. So in branch AC, in 2 ohm, current is flowing from A to C. Right? So magnitude and direction both are important. So in branch AC, I1 current whose magnitude is 0.4 ampere is flowing, and it is from A to C. So put this arrow from A to C. Then in CB, it means 2 ohm resistance. Which current is flowing? See the diagram. I2 current is flowing. I2's magnitude is positive. So our assumed direction, actual direction is same as that of assumed direction. So actual direction is also downward from C to B, right? So I2 is flowing in downward direction whose magnitude is 0.25 amps. It is flowing from C to B, right? So VAB would be equal to what? Or VTH. In some books VTH is designated as V dash. So V dash is equal to, take the algebraic addition, VAC plus VCB. So VAC is what? I1 into 2 ohm plus VCB I2 into 2 ohm, right? And see, this is positive, this is negative, this is positive, this is negative, right? So okay. Alright. Yeah. So I1 is 0.4 into 2, 0.8, I2 0.25 into 2, 0.5. So VTH is 1.3 volt. So Thevenin's equivalent voltage is 1.3 volt, which is also known as VAB. Okay, so we have obtained Thevenin's equivalent voltage, right? Now in step number 3, obtain the Thevenin's equivalent resistance, which is known as RTH, or it is also known as RAB. So RTH is what? It is the driving point resistance which is seen between the terminal A and B. And remember, while finding the Thevenin's equivalent resistance, you have to make the energy sources zero. It means if there is a voltage source, then voltage source is replaced by a short circuit, and if there is a current source, then current source is replaced by the open circuit. So in case of current, if you want to make the current zero, then open it. In case of voltage, if you want to make the voltage zero, then short it. Right? So remember these two facts. Okay, so now our circuit contains the two voltage sources. The two voltage sources are replaced by the short circuit. So this is first short circuit, this is second one, and the rest of circuit remains same, 3 ohm, 2 ohm, 2 ohm, 2 ohm, and A and B. Now between A and B, we have to find out the equivalent resistance, how much resistance exists between points A and B. Now again, in this complicated circuit, in the next step, when you want to find out RTH, first of all locate the principal nodes. First of all put the principal nodes in the figure. So in the next figure, yes, how many principal nodes are there? A, B. Then C and D. See this, C and D are short circuited. So actually C and D are not separate nodes, but both are the same nodes. So actually now this circuit contains only three principal nodes. They are A, B and C or D. So three principal nodes are there. So first of all locate the principal nodes, then one by one connect the resistance elements. So between A and C, 2 ohm. Between A and D, 3 ohm. A and D, 3 ohm. Between C and B, 2 ohm. C and B, 2 ohm. Between B and D, 2 ohm. B and D, 2 ohm. Right? And you should put the arrow so you can check whether all resistances have been considered or not. કસા રહી ના જવા જોઈએ. Okay. Right. Okay. So now between A and B, we want to find the equivalent circuit. Right. So try to reduce the network by series parallel combination or star delta combination. Now you can see that these 2 ohm and 3 ohm are connected in parallel. Why? Because these 2 ohm and 3 ohm are connected between the same principal nodes. Starting end of 2 ohm and 3 ohm are connected with A, finishing end are connected with node C or D. Both are same, right? So they are connected with the same principal nodes, so these two resistances are said to be connected in parallel. So its equivalent is 3 into 2 upon 3 plus 2, so 6 upon 5 ohm. Similarly, these 2 ohm and these 2 ohm are connected in parallel because both are connected between the same principal nodes B and D. So 2 into 2 upon 2 plus 2, 4 upon 4, so it is 1 ohm. So again the reduced circuit between A and B, this is 1.2, this is 1 ohm, this is C and D, right? First of all locate the principal node and then connect the resistances. Now between A and B, there is a single path, so both are connected in series. So equivalent resistance between A and B is 1.2 plus 1, so it is 2.2 ohm. So between node A and B, the resistance is RAB, or it is also known as R dash, or it is also known as the Thevenin's equivalent resistance, and it is what? 2.2 ohm. So finally we have obtained the Thevenin's equivalent voltage, we have obtained the Thevenin's equivalent resistance. So finally we draw the Thevenin's equivalent circuit in last step. So our original circuit between terminals A and B, right? This one, this between terminals A and B. So this circuit diagram, original circuit diagram, is replaced by the Thevenin's equivalent circuit diagram like this, like this. In this, Thevenin's equivalent voltage VTH, that is 1.3 volt, it is connected in series with the Thevenin's equivalent resistance, that is R dash or RTH or RAB, that is 2.2 ohm, right? So this is the Thevenin's equivalent circuit. And between A and B, now we will again connect the load resistance of 1 ohm, which we had earlier removed from terminals A and B. Now reconnect load resistance between A and B. So this is the complete circuit diagram, equivalent circuit diagram, equivalent Thevenin's equivalent circuit diagram. Now we want to find out finally the value of the load current IL. Now all voltages and resistances are available. So load current IL would be equal to VTH. There is a simple single mesh. So I is equal to V by total resistance, right? So IL is equal to VTH upon total resistance RTH plus RL. So IL is equal to VTH is 1.3 upon RTH Thevenin's equivalent resistance 2.2 plus RL is 1.3 upon 3.2. So IL is 0.4062 amps. This is the magnitude of the load current which is flowing through this load resistance of 1 ohm. And direction is downward. It is flowing from A to B. So always indicate the direction of the current, whether it is from A to B or B to A, right? So magnitude and direction both are equally important. If you don't indicate the direction of the current, then you may lose the mark, right? So this is the answer. So we have obtained the load current using the Thevenin's theorem, and it is equal to 0.4062 amps, and direction is from A to B. So now in the next lecture we will solve the same sum by using the Norton's theorem. Thank you.